Welcome back to this 8th lecture in the Programming Languages course. Today we'll be looking at prototype-based languages, and in particular we'll be using JavaScript as our running example. Outline looks like this for today. First I'll give you a bit of a general overview of class-based versus prototype-based languages, the key differences between them, and then we'll dive into the particulars of JavaScript. At the end, we'll have a quick look at some of the positive and negative aspects of JavaScript. The main source for the lecture today is the book JavaScript: The Good Parts by Crockford. Highly recommend the book. It's a very interesting read and it's quite compact. As a historical reference, I'd like to point you to the classic OOPSLA paper by Henry Lieberman on using prototypical objects to implement shared behavior in object-oriented systems, which gives a nice overview of the mechanisms used by prototype-based languages as opposed to inheritance in class-based languages. Now let's have a quick overview of some of the key differences in class-based versus prototype-based languages. First of all, I just want to remind everybody that the term Java in JavaScript doesn't mean anything. It was just a marketing ploy. In fact, officially the name of the language changed quite some years ago to ECMAScript, but that doesn't flow very well, so people continue to refer to the language as JavaScript. Now, when we think of object-oriented languages, we usually think of languages with classes. In fact, the first object-oriented language, namely Simula, introduced classes, objects, and inheritance as key mechanisms in Simula as add-ons to Algol. And Smalltalk, invented a few years later as the first pure object-oriented language, also followed in the footsteps of Simula. So the idea that a class is a repository or a template, a cookie cutter for creating objects, and that objects all belong to classes is fundamental in most object-oriented languages. Somehow, however, in the 1980s, various language developers, in trying to generalize and simplify object-oriented languages, came to the conclusion that the notion of a class wasn't actually fundamental. The notion of an object, however, was. And there were various experiments to develop new kinds of languages. In particular, there were extensions of Lisp, and there was also a successor to Smalltalk called Self. And these languages tried to show how, instead of requiring objects to be instances of classes, that one could start with the notion of an object as being the primitive, and that sharing of behavior between objects could be achieved in other ways, particularly by delegation. In such a case, one object could serve as a prototype for another, a prototype being an object that contains behavior that can be reused by other objects. So in class-based languages, classes serve two purposes. They serve the purpose of providing a template for creating instances, so they will create objects if you ask them nicely, and they're also repository for shared behavior. So an object has its own state, but when an object is asked to do something, its methods don't belong to that object, but belong to the class. So the object asks its class, hey, do you have a method for this? If the class doesn't, then by inheritance, the class will search up the superclass chain to find the method if one exists. So instances have exactly the properties and behavior defined by the class. Furthermore, the class of an object does not change at runtime. In a prototype-based language, objects contain both state and behavior. So there's no distinction. They just have properties. These properties may be instance variables or they may be methods. To achieve sharing, an object, if it doesn't have a particular behavior or method, it may be delegated to another object which serves as its prototype. So if you ask an object for a particular property, whether it's an instance variable or a method, that object will search, and if it doesn't have it, it will ask its prototype, and so on down the line. So in the end, with the prototype-based language, you can achieve a lot of the features of class-based languages. However, what's interesting is because any property of an object in a prototype-based language can be updated at runtime, you have a much more flexible and dynamic system. So that means that essentially the behavior of objects in prototype-based languages can be changed and extended at runtime. So instead of inheritance, we have the mechanism of delegation, and delegation serves as the mechanism for sharing behavior across multiple objects. So, summing up, prototype-based languages have no classes, so they're simpler than class-based languages. Everything starts with examples, so an object serves as an example or prototype for another object. We have fewer concepts. We just have objects and delegation without classes or inheritance, so the programming model is simpler. There have been quite a few experimental implementations of prototype-based languages over the years, but very few have been used outside of research. After JavaScript, perhaps the best-known language is Self, although there have been numerous others that have been used in practice, perhaps most famously Newton script, although of course since the Newton device introduced by Apple many years ago has not existed for a long time, it also is a defunct language. JavaScript, I would say, is the only one of the remaining languages which is highly used in practice. Of course, it's used virtually everywhere nowadays on any dynamic website. Let's have a look in particular how JavaScript is designed and how it works. So JavaScript was introduced in 1995 by Netscape. It has a very simple object model, so everything pretty much is an object. Functions as well are first-class objects, as are closures. We'll see exactly how that works shortly. The model of sharing is based on that of prototype-based delegation, so there are no classes in JavaScript, although as we'll see, there is a mechanism that allows us to simulate classes in JavaScript. The language is dynamically typed, so unlike Java, which is statically typed, JavaScript has more affinity to a language like Smalltalk there. It's interpreted, and it's supported on multiple platforms. Originally, the idea was that JavaScript would run inside your web browser so that you could use it essentially as a language for scripting the behavior of the web browser from within a web page. Since then, however, its usage has extended, so it's also used on the server side. The name Java was simply a marketing ploy. JavaScript has nothing per se to do with Java, aside from some superficial syntactic similarities. It is not, however, although it was originally thought of as being a language for scripting web browsers, that is not its only application these days, and JavaScript is also used on the server side. Syntactically, there's not too much unusual about the JavaScript language. We can see here, for example, that comments look pretty much like they do in languages like C and Java. Identifiers are also uncontroversial, as are literals. The first thing that looks a little bit different is the notion of object literals. So object literals are enclosed in curly braces. So open-close curly braces is an empty object. Here's a point with an X and Y property. Notice this looks very much like JSON. JSON is a format based on JavaScript for storing persistently the values of objects. The key difference in JSON, in the JavaScript object notation, is that the identifiers are always enclosed in double quotes. Otherwise, what we see here is the object literal notation is pretty much is very similar to JSON, and every JSON expression is also a valid JavaScript expression. Here we also see that we can have nested objects, such as this rectangle with upper left and lower right point positions. We also have in JavaScript function literals. So this is the notation for a lambda. So here we define a variable square, which is equal to a lambda function x with the body that computes and returns x times x. Array literals are uncontroversial. And we also have, interestingly, three equals operators. The first is the assignment operator, and then, as is usual in object-oriented languages, we have equality versus identity. So in Java, those would be equal and double equals, and this would be colon equals. Here, the equals is assignment. Double equals tests equality of objects, and triple equals tests the identity or strict equality of objects. Here we see a few examples where we access properties of objects, access and update them. So in our first example here, we see a book, which is defined to be the object with the title property. And we can simply access it by accessing book.title. Here we update book by assigning jdo, the string jdo, to the author property. So now if we query whether author is a property of book, now it becomes true. So this is different from typical object-oriented languages where Java, where you cannot at runtime add new instance variables or methods. Here we see how we can iterate over an object, look at all of its properties. And finally, we see that it's possible even to delete a property from an object at runtime. Methods are properties just like any other property. They're simply values that are functions. So here, for example, we have a counter, and the counter has a property which is its value. And now we add a new property, which is inc, and this inc is a lambda. So a function here that takes no argument and updates the value. Notice the use of this. This in JavaScript, so in prototype-based languages, functions the same as this or self in single inheritance object-oriented languages. This starts looking for the reference property in the receiver. So as we'll see later, when we have prototype chains, when we find a method that belongs somewhere down the prototype chain that references this starts looking again at the original receiver to try and find the reference property. So we're adding here an inc function to our counter. So now the counter has two properties, val and inc, and this.val will start looking in the counter for the val property. If it doesn't find it, of course here it does find it, it would continue looking down the prototype chain. We'll see shortly how that works. So now if we invoke the inc property, notice that the round brackets here are needed. If we don't include the round brackets, then we are simply referencing the inc property, which will return a function. To actually invoke the function, we have to add the round parentheses. Then, after executing that, if we access the val property of the counter, we'll find that it's updated to the value 1. Here, for example, we're accessing the inc property of the counter, but we're not invoking it. Instead, we're assigning it to f. If we ask what the type of f is, it's going to be a function. We can now invoke f, and this is going to be the same as invoking counter.inc. Here's a little example of how we can script a web browser. Here we see the HTML of a little web page, including a counter. So here we'll see the actual body of the web page, and the body includes a header, and the header has the value 0. The ID of the header is counter1. Now we have two buttons, a minus minus button and a plus plus button, as we see here. And on clicking, we will execute the following code: counter1.decrement or counter1.increment. The behavior is specified here in the script area, the script incantation here in the header of the HTML. And here we specify that this is JavaScript code. Originally, many years ago, when the script notation was introduced, the idea was that web browsers would eventually support multiple languages. In practice, essentially only JavaScript is supported, and other languages that are built on top of JavaScript, like TypeScript, or translated to JavaScript. Here we find the code. Notice that the code that we want to invoke is counter1.decrement or counter1.increment. Here's the counter. It has a value property, which is 0, and it has a name, which is counter1, and it has the increment and decrement functions. The increment and decrement functions simply do the update of the value, and they invoke update of this. What does the function update do? Well, it's going to access the DOM tree of this web page, and it will find the element which has the ID counter1, and that's this guy here. And it's going to set its value to the current value of the counter. So by clicking here, we will update the value of the counter and will also update the web page. Let's have a closer look at how delegation works now. So, as I mentioned earlier, delegation is the key mechanism, essentially the only mechanism for sharing data and behavior in a prototype-based language. So it completely subsumes the use of inheritance. An object, every object has a so-called prototype, and it may even have a chain of prototypes. This replaces the notion of a chain of superclasses in an object-oriented language. An object will delegate to its prototype object, for example, in the Mozilla interpreter, the way to access the prototype is through the property whose name is _proto__. Here, for example, we're going to create a new object, counter2, and counter2 will have as its prototype counter1, which we created a moment ago. This works by invoking object.create. This is a built-in to JavaScript, and this will create a new object with its argument as the prototype. So now we have a new object counter1 that has counter2, which has counter1 as its prototype. So that means counter1 is a completely empty object, but it has a prototype. So if we ask counter2 anything, that message will be delegated to counter1. However, we would like counter2 to have its own state. So counter2 is going to have a value, 0, and a name, counter2. And these now belong to counter2. The functions that were defined in counter1, the increment and decrement functions, we do not redefine, they continue to exist. So here what this looks like now we have counter2. It has a prototype, which is counter1. This is the prototype link. I've given it this stylistic kind of arrow because UML doesn't have a prototype arrow, so I invented one here. Counter2 has properties also value and name, which belong to it. and has as its prototype counter 1. If we now invoke the increment operator on counter 2, it will not be found here, but what will happen at runtime is that we'll follow the prototype chain and find the increment function over here. When the increment function is invoked, it wants to find the value feature in this. But remember that this refers to the original receiver. So when increment is invoked on counter 2, it will find not this value, but this one, the one belonging to counter 2. So this is exactly the kind of behavior that we would like to have. So this is essential. The key aspect then of prototype delegation is that this in the prototype is bound to the receiver of the original message. So when we invoke inc on counter 2, it's the value of counter 2 which is incremented and not that of the prototype counter 1. Now let's have a look at a little bit of a deeper look at how new kinds of objects can be constructed. We've seen one way, but there are actual multiple ways in which we can create objects in a language like JavaScript. A constructor is a special function in JavaScript that can be used with the so-called new operator to create objects. Here we have a function that's going to be used as a constructor. The convention here is that a constructor's name starts with a capital letter. So we introduce the name counter as capitalized name, and as a constructor it can take some arguments. The constructor's job, just like in Java, is to establish the invariant. So it's not a class invariant but an object invariant. And here what we want to do is simply initialize the value and the name of the object. The value gets initialized to 0 and the name gets initialized to whatever name we pass into the constructor. Now how is the constructor used? It must be invoked like this: new counter 3. If by accident you forget to call new, then you will just be calling counter as though it were a function. This can be disastrous. This will not create a new object. This will simply execute this code. This.val equals 0 and this.name equals name. But what is this in the global context? As it turns out, it's a special object, which is the window object, and it's going to get these properties silently. So if you forget new, that's not going to be a syntax error. JavaScript will do something, but it won't be what you expect. Actually, there are a lot of situations like that in Java. If you make a programming error, JavaScript will try and figure out what you want to do, may guess wrong, and will do something, won't raise an error, and you'll just get some strange behavior that you don't understand. Now, what this does is it's going to create an object, and it binds it to this in the constructor. By default, the return value is the new object. So this counter function doesn't have to explicitly return anything. So silently, the newly created object will be returned. So in this case, we start with an empty object, and this empty object has the property value and name added to it and initialized. By default, it will get a prototype which is provided by the system. We'll see that in a moment. So now if we access in counter 3, its value will get 0 and its name will get the string counter 3. When we create objects with a constructor, they all share the very same prototype. So every constructor has a prototype property which is automatically initialized when defining the function. So now if we want to make sure that instances created with that constructor have some extra behavior which is shared by them all we have to do is add those properties to the prototype. So here, for example, we can access counter.prototype and initialize its inc feature to be the same function that we had defined in counter1. Notice that the counter1.inc refers to this, so whenever it's invoked, this will automatically refer to whatever object is the receiver. So this will work beautifully. We can share methods from anywhere, and they should work as expected as long as the features that are referred to by this actually exist. So now we can copy those methods over from our original counter1 that we manually created to the prototype of our constructor. And now, once we've done this, notice we could have done that before we created counter2, or we could have done it afterwards, it doesn't matter. But now when we create counter3 with this constructor, which will initialize the value and the name for counter3, we will also, by delegation to the prototype, also get for free the inc and the dec methods. So now we can actually invoke counter3.inc. We couldn't before we added them to the prototype. And now, if we look at the value, it will have been incremented as we expected and as we hoped. Let's continue along and add some extra features to our objects. So now we're going to introduce a colored counter, and the colored counter here will have not only a value and a name, but it will also have a color, and that will be passed in to the constructor as an argument. Here we will set the prototype of the colored counter to be an instance created by our previous counter constructor. Since it's only going to be used as a prototype, it doesn't matter what its name is, so we'll create a new instance of counter with the name x. And now we get a picture that looks like this. We've created a counter x. It's being instantiated from the counter. It has its prototype, the counter.prototype. The colored counter has as its prototype a counter x instance, and blue counter then, when it gets instantiated, it will have as its prototype counter x. So now this is the prototype chain that we get. So blue counter will have as its prototype counter x, and counter x will have as its prototype counter.prototype. Notice in here, in counter.prototype, we have the inc and the dec methods because we assign them to the counter.prototype. This is going to be an instance of counter, and we're using it as the prototype for all objects created with the colored counter constructor. And this is an instance that we created with this constructor, and it will have as this prototype this guy. So now this guy has not only a value and a name, but it also has a color. And it also has some additional behavior which we've defined here. This is a magical onload function and is a kind of a callback. So whenever the window is loaded, whenever the page is refreshed, we will set the color of the element with this name in the web page to be that color. There's a little bit of funny stuff going on here. You might have noticed variable that equals this. Recall that this is magical. Whenever you invoke, when you try to access any feature by this, it's going to start looking at the original receiver. If we had used the word this here, then we'd have a problem, because within the context of window-on-load function, the receiver is not going to be our colored counter. The receiver is going to be the global window, and that's not what we want. So by assigning, however, this, that is, this being the instance of the colored counter, to the variable that, now we have a perfectly ordinary variable that we can pass around, and now that name is not the name of the window, but it's the name of our colored counter. And that color is going to be the color of our counter. So that's a little bit of a syntactic trick here to get around the fact that, to get around the special behavior of this. So, resuming, this is what the object model is going to look like. Here's our original counter object that we created manually. It was just a plain old object that we initialized using as an object literal. And whenever we create any object in such a way, it gets by default as a prototype object.prototype. Object is the default constructor that we used with object.create. These guys, all these constructors, know what their prototype is. So object's prototype is a default one. This is the end of the prototype chain for all objects in the system. Counter 2 we created with counter 1 as its prototype. So again, this is the prototype arrow. Counter 2 has the state, a value and name, and it has as its prototype the object prototype. We can see that here. It has as its prototype counter 1, and counter 1 is holding the deck and ink methods. So in a sense, counter 2 is kind of playing the role of the class for counter 2, but it's just a plain object. So it's a repository of these methods that we don't have to duplicate because they'll be the same for all objects. We had counter 3, which was created with the counter constructor. Every constructor knows what prototype it should give to its instances, and in this case the prototype that it gives to counters, so counter 3 that gets created is counter3.prototype. We explicitly copied in here the methods from counter 1. So we stole them and copied them here, so they'll be shared. So when we find them here, not over there, because the counter 1 is not in our prototype chain. Then blue counter is created with a different constructor. That constructor has as its prototype, not the default one that the system gives it, which would have been counter2.prototype, but we explicitly create an instance of this guy, which has as its prototype counter1.prototype. So that meant by overriding the default prototype for its instances, we got to reuse for free this behavior which we copied in from counter 1. So blue counter as well as counter 3, they all get through their prototype chains this shared behavior which we copied over from here. There's further shared behavior which is in here, which we haven't touched yet. But if you wanted to have behavior shared by all objects in the system, you could update, for example, that guy. The picture here isn't complete. We've just looked at these guys which we created, but everything else in the system is also an object, and every object in the system has a prototype, and eventually inherits from, delegates to object.prototype. There are lots of predefined objects in the system like array and boolean and date and so on and so on. The end of the prototype chain for all objects in the system is object.prototype. So if you wanted to add a property to all objects, you could simply add one here. So here we've added an inspect feature to object.prototype, which is in a function that will raise an alert. So here the alert will essentially print that object and make it available to us. If, on the other hand, you wanted to extend some built-in functions, prototypes of the system, built-in objects of the system, like arrays. So suppose I wanted to add to every array in the system a map feature. Well, I would simply add it to array.prototype. So here's the map function, which is pretty much like the map function in Haskell, which will, it's going to be a lambda that takes as an argument a function and applies that function to every element in that array and returns the new array. So here, for example, if we take an existing array, and now we can map the floor function to the array and get a new array, which truncates the decimal part of all of these values and gives us a new array. Or if we map the lambda x plus 1 to all of these guys, then we'll get a new array with each of these values incremented by 1. Something that you don't see in too many programming languages, but there are a few that support something similar, is the possibility to have additional hidden arguments to functions. So languages like C provide you ways of doing that, and Python as well. JavaScript supports it in the following way. If I define a function, like this one, concat, which will concatenate, which will use a particular separator to concatenate an array of arguments, we would like this concat function to take as its further arguments an arbitrary list of things to be concatenated together. Well, there's no way that we can specify here separator ... What you do instead is we just mention separator as an obligatory argument, and then the rest of the arguments are accessible in a variable called arguments, this magical argument. Of course, the very first position in arguments is the first argument here, which is named explicitly, but the rest of them starting at position 1 can be accessed from position 1 to the actual length of the argument. So now, if, for example, we invoke concat with semicolon as the first argument, and then red, orange, and blue as the remaining arguments, then we will get as the output red, orange, blue concatenated together, joined together with a semicolon as a separator. There is a further trick, which is very specific to JavaScript. Suppose you want to access the currently executing function itself as an object. Well, you can't access it using the term this, because this would refer eventually to any receiver to which this function is being executed as a feature. So in order to be sure that we can actually access the function itself, there's another way of doing that. And it's also hidden in the arguments variable under the property callee. So the callee of the arguments is the function itself. Here we use it to, because every function is also an object in JavaScript, to add a feature and update it within that function. So here's a function. The first time it's called, we will see if there is a count feature, a count variable. If it doesn't exist, we're going to create a new one and initialize it to 0. If it does, and then once it's been initialized, so if it does exist, after the statement it will exist, then we simply increment it. So if we call f 3 times and then ask for f's count value, then we'll get the value 3 back. Now let's have a look at closures, which have a particular affinity to the lambda calculus. The scope of a variable is the region of the program in which it is defined. Now it's important to understand the concept of lexical scope. So lexical scope, or static scope, is the scope of a variable according to the text of the program. So it's completely determined statically. You can look at it at compile time without executing the code. This is different from dynamic scope, which is generally avoided in programming languages because it can be extremely confusing. In JavaScript, there are essentially just two scopes. One is function scope and the other is a global scope. We do not in JavaScript have block level scopes like we have in most other languages like Java. Here we have some JavaScript code where we have a global variable x, we have a function defined called f, and within f there's a nested function g. F defines a variable y, and g defines variables x and z. Within f we initialize y, we define g, and then we invoke g. And then we can invoke f in the global scope. Now what's going on here? In the global scope we have a variable x, so we have an environment here with x defined. Within f we have another environment, and in this environment y is defined with value 2. Then we have function g with variables x and y. Within the global scope we only see this environment. Within the scope of f we see our local scope, but we also see the global scope. Notice the affinity here with dictionary stacks in PostScript. This is a dictionary, this is a dictionary, and now we have a stack. The stack is growing down here instead of growing up, but it's the same thing. Every time we enter a new scope, we're pushing a new dictionary onto the stack. And when we look things up, we start looking up from the top, here the bottom, of the stack. So within the function g, if we're looking for the variable z, we'll find it immediately. If we're looking for the variable y, we start looking in our nested lexical scope. We don't find it here, but we'll find it there. If we're looking for the variable x, we will find it immediately. Notice that this x is hiding or masking this x. So when you define a variable in a more refined scope, it may hide a variable that's in an outer scope. And that's perfectly fine, or in some languages it may be considered an error or a warning. So functions are lexically scoped. They are not dynamically scoped. What would dynamic scoping mean? Well, dynamic scoping would mean that when you invoke a function, what the stack of dictionaries you would see is not the lexically scoped dictionaries, but the function would get the scope of whichever function it was called from. This is extremely fragile. Once upon a time, there were languages that adopted dynamic scoping, and people very quickly realized that this was a very dangerous and confusing feature that leads to a lot of confusion. As a consequence, when you execute a function, it's always executed in the scope in which it's defined or created, not from the one in which it's called. Virtually no programming language today supports dynamic scoping, at least none that I know of. It's generally to be avoided. Dynamic scoping does exist, but not for variable names. Dynamic scoping is exactly what you get in exception handlers. When an exception is raised, the handler that's in place is not the lexically scoped handler, but it's the handler of whoever called you. So if I am a caller and I have a try-catch clause in Java, and I invoke an arbitrary method somewhere else, and if that method raises an error, the handler that will get triggered is not the handler of the lexical scope of whatever that code is, but mine that was dynamically created in the try-catch clause. So that, to my knowledge, is the only case in modern programming languages where dynamic scoping is in place, but it's not for looking up variable names, it's for dynamically looking up exception handlers. Now, a function which is nested is always executed in the scope in which it's created. These inner functions are known as closures. Now, you have to think back to the lambda calculus. In the lambda calculus, we may have nested lambdas. Every lambda which has names, these names are bound either by the lambda itself or by some enclosing lambda. This is exactly the same thing in Java. So any name that occurs in a nested function is bound in the static scope of its enclosing lambdas or functions. Here's an example. I have a function f, which takes an argument x. It locally defines a variable y with value 1. And now I'm returning a function. So this is a lambda returning another lambda. And this lambda takes no further arguments, and it computes the value of x plus y and returns that. This x is the x that's the parameter to the function f, and this y is the one that's defined here locally within the scope of the function f. The thing that's returned is a closure, and it's bound to this environment, the environment of the function f. Even if the function f returns and is gone, the environment continues to exist. Now, this is critical. So here I invoke function f with argument 2, and I get a value back. This value is a function, and that function is a closure. It's a closure because there's the function body, and the body is closed by the environment that it had when it was created. So now if I define a global variable y of value 99 and invoke closure, the closure will not see this global y. It'll only see the local one of its local scope. In other words, this expression here with the free variable y has been closed by this environment. So that's why we use the term closure, because we're closing a lambda with closing it by binding its free variables. So the key thing that's important is even after f has returned, the scope of f continues to exist even after f has returned. Here we can visualize that further. Here's the function f. In the lexical scope of the function f, within there, we define a function, a lambda, that returns x plus y. And here's the global scope. Here's the scope of the function f with its scope of x and y. These are the ones that are defined here. And this function here, it doesn't add any further variables, but the scope of the function that we return is going to be this. So this is its visibility. And notice that this y is going to hide any eventual global x's or y's. So this is why when we invoke the closure, it's going to see this scope which continues to exist after f has returned. Now we can do a very cool thing with closures. And this gives us the ability to fully encapsulate and protect objects in JavaScript. Notice that JavaScript, when we created an object, we can have these nested objects with the curly braces. Every feature of every nested object is completely public and publicly accessible. So it seems that the basic mechanisms that JavaScript provides us don't allow us to hide or encapsulate internal data. Well, in fact, there is a way to do it, and the way to do it is with the help of closures. Because a closure contains variables, but these variables are part of the environment of any functions that we may have, but this environment is not accessible from the outside. It's only accessible to the lambdas that have been defined within its scope. So now here's a cool thing that we can do. We're going to define now counter 4, and counter 4 is going to be the result of invoking a function here. So here's the function, and here we invoke it with the parameter counter 4. What does the function do? Well, the function is going to return an object here, and that object will have an increment, a decrement, and a val and a name features. The increment and the decrement functions are pretty much as we saw them before, except val refers to a value in the scope of this nameless function that we invoked and threw away. So there's a lexical scope here with a value and a name, and the name is initialized to counter 4. This scope exists, and it's only used to close this object. So this object has an environment containing the val and the name, which are not accessible to anybody from the outside. In addition, we provide getters. So this is a feature that was introduced in ECMAScript 5, and the getters allow you to get a value, but you can't modify them, so it's not a variable. We could equivalently define a function that just returns the value, but doesn't provide any ability to update it. But it was decided that this was so important to have immutable fields that this would be the way to do it in JavaScript 5 or ECMAScript 5. So now when we return counter 4 and inspect it, we see it has decrement and increment functions, but name and val are simply getters. They are also essentially function which will return these values, but they are getters, so there's no way of setting or updating these values from outside. So this is the way that we can hide or protect values. Furthermore, we could have additional variables here without any getters, and they would be completely hidden from the outside. Fine. Now we've seen numerous ways of creating objects, starting from manually creating objects as literals, to using the object create method to clone objects with a given prototype, to using constructors to create something like a class-based instance in JavaScript, to finally seeing how with closures we can actually encapsulate and hide internal variables of objects. Now let's have a look at a bit of an extended example of snakes and ladders. This is an example if any of you took the Introduction to Object-Oriented Programming course P2 with me, you will have seen the snakes and ladders example in Java. If you refer to that course, you can see how the implementation is done in an object-oriented way with Java. Now we'll see how we can do the same thing in a slightly different design using JavaScript. The Snakes and Ladders game is a trivial game that kids like to play when they're very young, and it helps them to learn how to play games that have well-defined rules. So the game is kind of boring, and the idea is that players will start on an initial square. They take turns rolling a die, and they move forward the number of places that the die indicates. The first one to land at the finish place wins. If you land at the bottom of a ladder, you go up to the top of the ladder. If you happen to land at the head of a snake, you go down to the tail of the snake. And if you land on a place where there's already an existing player, then you will jump back to the beginning. The game is moderately fun for little kids because they learn how to play a game according to these strict rules, but it's very boring once you start playing other games and you realize that there's no room for strategy. So nothing you can do will influence the outcome of the game. It's only the roll of the die. But this is great for us because we can implement now a computer game which is completely closed and doesn't require any input from the user except rolling the die. Now, let's see how we can implement this game in JavaScript using the concepts that we've seen so far. First of all, we want to apply design by contract, so we'll need some way of checking assertions. So we'll define our own assert method. The last time I checked in JavaScript, there was no built-in assertion mechanism, so we'll just define one. If the expected outcome is false, then we're going to post a debug message and throw an exception. As follows. The details are all there in case you really want to know. Now, we want to be able to create a game and encapsulate as much as possible. So when we create a new display, we're going to take as input 3 pieces of information. There are 2 players and a configuration. And the configuration will specify the configuration of the game. In particular, the number of rows and columns. We will also get an image from an image file that will load in that shows a display of the game and further information. We'll also get from JavaScript access to a two-dimensional canvas that we can actually display things on. There's a fair bit of junk in here that we want to hide, so we put it all in a scope, an environment, and the functions that we return, namely there's going to be a test method and a repaint method. These will have access to all of this information. Here's the repaint method, and it has access to the variables in this scope, and they're otherwise hidden. So we will only return the public fields. In order to create a new instance of the game, then a display we just call make display with the configuration and players Jack and Jill. Now, in a web application, there's a certain amount of asynchrony because there are things happening on the client side, but also on the server side. In particular, the various files containing images that we're using are going to be loaded asynchronously. So in order to make sure that everything works correctly, we need the use of callbacks to know when a particular action has completed. So this is the onload function. So we define for an image or for a piece an onload function which will be invoked once the files have completed loading. So when we've loaded the image representing one of the pieces that move on the board, for example, then we'll compute its size and shape so that we know how to properly display it. Now, in the original implementation of the game, we had a square class and a square interface actually, and we had several different kinds of squares defined as classes in an inheritance hierarchy. So different kinds of squares would be a first square versus a plain square because they have different behavior. In particular, the first square can have any number of players on it, whereas a plain square would allow at most 1. And a ladder or a snake had a special behavior if a piece lands on it. And finally, the last square is important because it knows it's the last square, so it knows if a player lands on it that somebody has won the game. So this was defined as an inheritance hierarchy. Even though we can simulate classes in JavaScript, we would rather take full advantage of the language and have a design which exploits the prototype-based mechanisms that JavaScript provides. So instead, we won't have an inheritance hierarchy, because we don't really have classes. Instead, we'll have prototype chains. So here, we start with the first square. So the first square has a particular position. A piece can land there. we can make a move, we can ask the square if it's the last square, or a player can enter or leave a square. So we define first square as a prototype, as an object literal, so it has its position 1. If we try to land on the square, we will always land on this square, whereas if we land on a ladder, we'll actually land somewhere else. If we want to enter the first square, that's never a problem, so we don't have to do anything special, whereas if we enter another square, we'll have to check if there's another player there or not, and that may cause something special to happen, and so on. So this is going to be our the first square that we define. Now, by incremental modification, we can define a plain square to be like a first square. So we will clone first square using the object.create method, which will make first square the prototype for plain square. Now all we have to do is update the features and methods that are inherited by delegation to be the ones that we need for a plain square. So plain square has at most one player that is currently there. So even though we don't like nulls, we'll represent the fact that there is no current player on the square by the value null. And when a player enters the square, then we simply set the player to be the player that's entered. Ideally, we should have an assertion here asserting that the player is null. And if we leave, then we set the player back to null again. A ladder is a further refinement of a plain square, and it has the additional behavior that if we try and land on the ladder, then we're going to be transported forward a certain number of squares. The last square is also special. It's just like a plain square, however it knows that it is the last square, so instead of returning false, like the first square would, it will return true. And now we've got our whole prototype chain. We'll skip the implementation of a snake because a snake is simply a ladder in reverse. Now we'll use JSON to define some configurations. Here are two different snakes and ladders games. This is a simple one with 3 rows and 4 columns. We have a board that's specified in a PNG file, and we also have a couple of pieces that can play on the board also in separate files. We define on the board 3 ladders. One is a ladder that goes from position 2 forward 4 squares, 1, 2, 3, 4, to square number 6. Another one at position 7, which goes forward 2 squares to position 9. And another one, which is actually a snake, which goes from position 11 backwards 6 steps to square number 5. So we don't need a separate snake, we just model it as a ladder. Of course, on the board, it's displayed as a snake, but internally for the logic of the game, it makes no difference. And here's a second game, which happens to be 6 by 6 with a different PNG file, the same player files, and a whole bunch more snakes and ladders than we had before. This is all specified as JSON, which looks pretty much like an object literal in JavaScript, the only difference being that all these names have to be enclosed in double quotes. Now what we can do is we can interpret this JSON by loading it into our application. Here we take the configuration as an argument to make board, and we simply walk through it identifying, so the first square, so we initialize our board to the number of rows and columns that we need. The very first square is going to be the instance that we have already. We already created first square. We don't need multiple instances of first square, so there's no need to clone it. We just directly use it. Plane squares will need multiple instances of them, so for every plane square on the board, we'll clone it using object.create. Now we've completely initialized the board, where every square except the first square is a clone of plane square. And now we're going to walk through the ladders and overwrite those, everyone that's a ladder, by a clone of the ladder instance that we have. And finally, at the end, I don't show it here, the last square gets initialized to the last square instance that we created. Once again, we're going to return a closure, so we'll simply return the closure with the bits and pieces that don't need to be hidden anymore. So, namely the size, the squares, the find, and the home methods. Now we have to create Jack and Jill. We're a little bit old-fashioned here. We create Jack first as an object, and then Jill is going to be a clone of Jack. But if we want to be a bit more modern, we should have created Jill first, and Jack could be a clone of Jill. It's all the same. The point is that we only need to create one object, and the other object can be a clone of the first one, and we only need to update the particular features which represent state that is unique to that object. So in this case, Jack and Jill have the same behavior. They have a move function and a wins function, and they have instance variables name and square, which the name gets initialized once and then no longer updated, and the square is a value which changes every time the object moves. At the top level, we can define the game as an object, and it has players. It knows when it's over. We can swap the players, and we have a move function, a top level move function. As long as the game is not over, we can roll the die, and we can make the player move. Check if the player wins. If the player does win, then we update the isOver variable to be true, and we output whatever status and swap turns. And if the game is over, then we stop and simply report that the game is over. At the very top level, of course, we have the HTML files. We have our canvas. We load in the code of the snakes implementation, which is in a separate JavaScript file. We're going to make use of jQuery. It will help us to, we'll use functions from jQuery to initialize and load the game. And then the new game function is going to be initialized here, and the new game will load our configuration, initialize Jack and Jill, and start the game. So that essentially is the complete story. Let's have a quick look at what the game looks like in practice. Just for fun, let's have a look at how the game looks in a web browser. Here we've loaded the Snakes and Ladders game into Chrome and activated as well the JavaScript console. Here we've got one version of the game here, so the 3x4 game. So here Jack rolls a 5 and ends up in position 6. Jill rolls a 4 and ends up at the bottom of the snake. Jack rolls a 4, ends up in position 10, and so on. In the JavaScript console, we can inspect these objects. For example, we can have a look at Jack, and we can see that Jack is an object with a name, and its current square is position 10. We can also see that his prototype, because he was an object literal, he gets for free the prototype, which is the object prototype. If If we look at Jill, on the other hand, since we see that her name is Jill, she also has a position. However, since she was cloned from Jack, we see that her prototype is Jack and Jack's prototype is the object prototype. We could also inspect game and see that the current player is right now Jill. We could also directly execute the game method from the console rather than using the move button. And here Jill rules a 4 and ends up on square number 5. Finally, we can load in a completely different game, such as this 6x6 board, and play it just as well. To conclude, let's have a quick look at some of the nice features and some of the scarier features of JavaScript. Now, there are lots of features we've seen, like object literals and the use of JSON, which work very nicely. Also, the object.create method works very nicely to create a prototype-based design. So here you're cloning objects to create a chain of prototypes, exploiting delegation to share behavior. You can also dynamically update objects to add new features or remove features, and this can be very powerful. The fact that we have first-class functions and that functions are lexically scoped and that we can return functions within functions which are closures is also very powerful and gives us a nice encapsulation mechanism. There are some not so nice features, particularly globals. Globals tend to be evil. As we mentioned briefly, we saw that global variables belong to a special object known as window, and if you are executing a function that doesn't have any particular receiver, then that function will belong to window. So in particular, if you have code like we see here on the right, here we have a function that refers to this.color. This is not going to work well because this.color doesn't refer to the color of the new object that you're creating, is going to refer to this of the window. And that's why we had to play the game earlier by assigning that, this to that, in order to get around the magical behavior of the this keyword. Furthermore, if you execute a function like a constructor without calling new, or any function that's in a global context, then any references to this that might be there will actually refer to the global window object. And if you refer to a variable that doesn't exist yet, it will magically be created in the global scope. So undeclared variables will become new globals, which is not nice. As we've seen, we have nested lexical scopes for functions, but there are no block scopes, which is a shortcoming. In all fairness, ECMAScript 6, JavaScript 6 fixes some of these, for example, block scopes, but that's not the case in older versions of JavaScript. And there are still numerous other issues which are still open. Most of the items that I've listed here are from the book Java, the JavaScript, the good parts. So one of the issues that are mentioned is that arrays are not real arrays. So in fact, they're objects and they're not implemented in a very efficient fashion. Function arguments are also not arrays, they're just objects with a length property, which also can cause some issues. For in loops don't work very well with arrays. JavaScript tries as much as possible to do reasonable things if there are errors in your code. In particular, if you forget to insert semicolons in reasonable places, it will try and do it for you. But sometimes, and there are examples given in the book, that it does the wrong thing. JavaScript also tries to do clever things with type conversions and guessing of the types that certain things should be, but this leads to confusion as well. So the type of operator, for example, says that null is an object, not the null value. That's not very helpful. And the equals equals operator does weird things when it sees an argument that's not of the type that it expects. It tries to coerce that value to a value that it thinks makes sense, but it's not symmetrical. So if you say A equals B and the types don't match, it might try and convert B, but if they're reversed, something else will be the result. In such cases, probably what you want is to use the identity operator rather than equality, so the triple equals. Calling constructors without new will also give you very strange results, as mentioned before, because it's simply going to execute the function rather than creating a new object. And finally, some other nasty things. There's no standard so far for setting the prototype of an object. The __proto__ convention is specific to certain browsers, and there is in the metaprogramming API no standard setter for it. Another problematic issue is you can only have a single chain of prototypes, so that gives you the same restrictions that you have in single inheritance languages, and that sometimes makes it hard to model the behavior that you want. So there's no multiple delegation. Instead, the only thing that you can do is if you want to inherit, if you will, or delegate to multiple prototypes, you can only delegate along one chain, and you will instead have to copy in the other features that you want from another location. So this is similar to what you have to do in Java when you can inherit from one class and have to implement another. Then the one that you implement, you have to somehow copy or duplicate or repeat the methods or features that you want to reuse. Finally, the new keyword that allows you to, that simulates class-based behavior in class-based object-oriented languages is actually confusing the programming styles. So it is essentially kind of a SOP to people who are expecting in JavaScript to program in an object-oriented way rather than a prototype-based way. It kind of simulates class-based programming, but not completely. Instead, what would be much better is to acknowledge the fact that the paradigm is different. You're not programming with classes. So instead, try and program with prototypes and use object.create instead. Use cloning rather than subclassing, and use delegation rather than inheritance. Okay, thanks very much for your attention.